In this lesson, we're going to show different strategies of solving quadratic equations and some applications involving solving quadratic equations. What is a quadratic equation? Any equation of the form ax squared plus bx plus c is called a quadratic equation because the highest degree of x is 2. We'll work only with quadratic equations that have real coefficients a, b, c, and in order to be quadratic, the coefficient a must be different than 0. What are the ways of solving quadratic equations? Well, we'll learn already quite a few of strategies that will allow us to solve quadratic equation. For example, the first such strategy would be factoring. If we have a quadratic equation x squared minus 4 equals 0, we could solve it by factoring. So this is difference of squares, it factors into x plus 2 and x minus 2. And then we're going to use zero product property, zero product rule. Let's recall what's zero product rule. Well, if you have two quantities and you multiply them and the product is 0, then either the first quantity is 0 or the second quantity is 0. Therefore, to complete the solution for this equation, either the first bracket is 0, which means x is equal negative 2, or the second is 0, which gives me x equals 2. We can say that the solution set to this particular quadratic equation consists of two numbers, negative 2 and 2. So we can write solution set equals negative 2, 2 in a wavy bracket like this. Our second example consists of three terms. So we also have this linear term, 2x. This polynomial is still factorable because the product of outside terms is negative 15 and the difference is 2, so 5 and negative 3 should work. To factor it, put two brackets. We know that product is negative 5, so let's say one number is 5, the other is 1. We must have different signs. I don't know which one is negative, which one positive at that moment, but I keep this in mind, two different signs. The leading term is 3x squared, so we must have 3x and 1x. I don't know in which order yet. However, I need to keep in mind that the inside product and the outside product, when put together, should give me 2. They should differ by 2. So if I multiply 5 times 1x and 1 times 3x, these two products will differ by 2. I need to end up with a positive 2, so 5x will be positive and 3x would be negative. So this is your factored form, and now we can easily rate the roots. From the first bracket, x is either 1, or from the second bracket, when you solve it, you get 3x equals negative 5, therefore x equals negative 5/3. So we have two roots, 1 and negative 5/3. We can give the final answer in a set notation. The solution set consists of negative 5/3 and 1. So that's a well-known strategy by factoring and by using zero product rule. How else can we solve quadratic equations? Another method is called square root property. And this method works very well in the first example. Instead of factoring it like before, we could put the 4 to the other side and then apply square root on both sides of the equation. Now let's recall that square root of x squared is not just x. It is actually absolute value of x. So instead of root of x squared, we'll write absolute value of x equals, and square root of 4 is just 2. Now, quite often we skip this step, and instead of writing absolute value of x, we write at once x equals plus or minus 2. So remember, either absolute value or plus or minus on the other side. So yes, we've got the two solutions as before, as we expected. So as before, the solution set to the above equation is negative 2 and 2. In the following example, we can notice that the left-hand side is always positive or 0. However, the right-hand side, as you see, is negative. So it's impossible to have a quantity that is non-negative to be equal to a quantity that is negative. Therefore, these two sides will never be equal. So what this really means is that we have no solution in real numbers. However, if you would like to solve it in complex numbers, what we should do, we should follow the strategy as before and take square root on both sides. So we'll have square root of x minus 1 squared equals square root of negative 4. And again, square root of something square is really absolute value of this something. And square root of negative 4 is the same as 2i, because this is like square root of 4, which gives you 2, and square root of negative 1, which gives you I. Now, to drop the absolute value, we'll write x minus 1 equals plus or minus 2i. And finally, move the 1 to the other side, and yes, we have a complex solution, 1 plus or minus 2i. So the final answer for this question in complex numbers would be the solution set is 1 minus 2i and 1 plus 2i. In real numbers, we have no solution. In complex numbers, we have two solutions. The following method of solving quadratic equation is called completing the square method. What we want to do, we want to bring the general case of quadratic trinomial to the previous case when we had something square on one side and a constant number on the other side. So we would like to complete the square by looking at the first two terms. The first step in this process would be to move the free term to the other side. So isolate the constant term. The next step would be to divide by the leading coefficient. In this particular example, we don't have any leading coefficient, so we can skip this step. But in the following example, if we had a 2 in front of x squared, we're going to divide by it. The following step would involve completing the square of these two terms with x. How do we complete the square? Well, we do it by following this rule. We're drawing a perfect square of a bracket, and in the bracket, we take the x, we take the same sign as before, and we take half of the middle coefficient, exactly half of this coefficient b. So in our case, I draw a bracket, square it, I take the x, the same sign, and half of this middle coefficient, which is 1. After squaring, I need to subtract perfect square of that number, so subtract 1. So why this rule really works? Here we have a little applet that will justify geometrically how come this formula works. We're taking a yellow square with the side x. The area of this yellow square is representing x squared. And here we have a blue rectangle with one side equal to x and the other side equal to b. If we divide this rectangle in half along the side x, then we obtain two rectangles with sides x and b half. So let's try to move these rectangles and attach to the yellow square x square with aligning the second blue rectangle along the other side of the yellow square. Now the area that we have here is really x squared plus bx. So this is what we started with when we try to complete the square. What we want to do is make a nice square by adding this little square that is missing here. This way, with the orange little square, we have a perfect square of x plus half of b. However, because the original expression consists only of yellow and blue, then we have to, from the big perfect square, subtract the small perfect square, which is a perfect square of half of the b. We can notice that this would work no matter what the b is. The b could be smaller or larger, doesn't really matter. We still have the same idea. So as we saw, the x squared plus bx, which is the total area of the blue shapes, so totally this and this is bx, is the same as x plus b half. So x plus b half is this distance, square it, but then we have something extra. We have this orange square, which is extra, and we need to subtract it. So this orange square, that's the part which is b half squared. Let's come back to our example. Now what we need to do is to bring the 1 to the other side and add it to 5. And finally solve by square root property. So we can apply square root on both sides of the equation, and that will give us x minus 1 equals plus or minus. Always remember this plus minus sign that will indicate two roots. So x equals, bring the 1 over, and you have 1 plus or minus root 6. So what we've done, we solved the resulting equation by using square root property. And finally, we can state the solution set as two possible roots. This could be written with plus minus sign, or equivalently you can write 1 root, comma, and then the second root with plus. Okay, let's practice the procedure of completing the square on the second example. So as before, we are going to move the 1 to the other side. We have 2x squared plus 3x equals 1. And now, since the leading coefficient is more than 1, we're going to divide by the 2. So as before, we are moving the 1 to the other side, resulting in 2x squared plus 3x equals 1. And now, since the leading coefficient is more than 1, we are going to divide by it. So divide by 2. Even though we end up with some fractions, don't worry about it. Fractions are good to calculate. So we end up with x squared plus 3 halves x equals 1 half. Now we complete the square of these two terms by following that rule. That means prepare a bracket, take the x, take the same sign, take half of the middle coefficient. So it will be half of 3 halves. To take half of a fraction is enough to put extra 2 in the denominator, so you really have 3/4. And square it. Now, since this perfect square gives us really more than we had originally, we need to subtract perfect square of the number that we took in the bracket. So subtract perfect square of 3/4. This is the extra orange piece on the diagram. We need to subtract it in order to match whatever we had originally. And that equals 1 half. And the final step would be to solve it. That means bring the three numbers to the other side and use square root property. So we have 1 half plus, and square of 3/4 is 9/16. Now, in order to be able to add these two fractions, we need to extend the 1 half to the new denominator 16. So multiply the top and the bottom by 8. Therefore, we end up with x plus 3/4 squared equals 17/16. And finally, when we take square root on both sides, we end up with x plus 3/4 equals, remember, plus or minus. And now we can split the square root of the numerator, root 17, over square root of denominator, which is just 4. Notice that at this moment we already have the same denominator, so it will be easy to combine these two fractions. We end up with x equals, on the same denominator 4, bring the 3 over, it's negative 3, plus or minus root 17. So that will be the final answer. And we are ready to state the solution set. Solution set is these two roots, negative 3 plus or minus root 17 over 2. The last method that we can use to solve any quadratic equation is by using quadratic formula. This quadratic formula really comes from completing the square of the general form of a quadratic equation. So how does it work? Well, your coefficients by x squared, x, and a free number, those are your a, b, and c. So let's list. A is 3, b is 2, and c is negative 5. So we find the roots just by following that formula. Negative b plus minus square root of b squared minus 4ac, everything over 2a. This is a formula that will need to be memorized, so try to use it as often as possible to remember it. How does it go? Well, x, sometimes I use subindexes 1, 2, because we predict that there will be 2 possible roots, equals negative b, so it's negative whatever the b was, so it's negative 2, plus minus square root of b squared, which is 4, minus 4 times a, which is 3, and times c, which is negative 5. Everything is over 2a, 2 times 3. And let's simplify it according to order of operations. So we have negative 2 plus minus square root of 4 plus, and this is 60, so it's 64 over 6. Now, here we are quite lucky because root 64 is easy to calculate. That will be negative 2 plus minus 8 over 6. And since these two numbers can be added or subtracted, let's do it. Negative 2 plus 8 is 6 over 6, which gives you 1. Or negative 2 minus 8 is negative 10 over 6, so it's negative 10 over 6, that can be simplified to negative 5 over 3. Therefore, our solution set is composed of two numbers, negative 5/3 and 1. Okay, we've been using quadratic formula, but how come someone come up with this formula? Well, we can actually develop the quadratic formula just by completing the square procedure. So we start with a standard form of quadratic equation, ax squared plus bx plus c equals 0. And what did we do first? Well, we moved the free term to the other side. So we end up with ax squared plus bx equals negative c. Then we wanted to have leading coefficient equals 1. So let's divide by a. That gives us a squared plus b over a x equals negative c over a. The next step would be to complete the square of these two terms. So we write a bracket, we're going to square it. In the bracket your x, the same sign, and half of this middle coefficient, which is b over 2a. Now, since this is more than what we had originally, because that's a perfect square, end up with 3 terms and we had only 2 terms, we need to subtract from it, diminish it by the last term square, which is b squared over 4a squared equals, and in preparation for the same denominator, let's rewrite the negative c over a as negative c over a, but we also would like to multiply the numerator and denominator by 4a. So that will be 4a squared. That way we produce the same denominator and it will be easy to combine them in the next step. So we end up with x plus b over 2a squared. That equals, under the same denominator 4a squared, we bring the negative b squared to the other side, making it b squared minus 4ac. So you can notice this is already this radicand in a quadratic formula, b squared minus 4ac. Now we take square root on both sides of this equation, and we end up with x plus b over 2a equals plus or minus square root of the numerator, which is b squared minus 4ac, over square root of the denominator, but denominator is already perfect square, so that becomes 2a. And here again we can notice we have the same denominator, which is nice, it will always work like that. So we may end up with the final answer, x equals, bring the b over 2a to the other side, under the same denominator, that becomes negative b plus minus square root of b squared minus 4ac over 2a. So we really have the quadratic equation here. That means it doesn't come from the heaven, it comes directly from completing the square procedure. Quadratic equation allows us to investigate properties of solutions. For example, we don't necessarily have to find the solutions in order to tell if the quadratic equation has a real solution at all, and if yes, then how many of them, either one or two. How can we do that? Well, just by checking the radicand under the root b squared minus 4ac. This radicand is called discriminant because it determines what kind of solutions we should expect. This determinant will be often denoted by a Greek letter delta. So how can we tell what type of solutions do we have? So let's recall again quadratic formula, negative b plus minus square root of b squared minus 4ac over 2a. So notice that because of this plus minus, as soon as discriminant is bigger than 0, as soon as delta is bigger than 0, we will have two possibilities, two roots, one with plus, one with minus. So if delta is bigger than 0, then we have two distinct real solutions. If delta is exactly 0, so we really have negative b plus minus 0, that doesn't change anything, so it's like minus b over 2a. That tells me that I have only one real solution. This solution is called double. Why it's double? Well, just because any quadratic equation has two roots, and if we have only one value, we're taking it twice. It's like solving equation of the type x squared plus 2x plus 1 equals 0. That's a perfect square, so you can fold it back to the square of x plus 1, and you end up with one double root, which is negative 1. Why is it double? Because there's two brackets and negative 1 comes from each bracket. Therefore, negative 1 appears twice in factored form. The third possibility is that determinant could be negative. If the determinant is negative, then we have a root of a negative number, which is really a complex number. So we end up with two distinct but non-real solutions. So we don't have real solutions, we do have complex solutions. The other advantage of using the delta sign is to make the quadratic formula a little bit shorter. So if we remember the discriminant delta b squared minus 4ac, then the quadratic formula takes this form, negative b plus minus square root of delta over 2a. And one more property that we could derive from observing just discriminant delta. If this discriminant is a perfect square, then what's happened, we actually can calculate the square root of it. Remember the previous example when we had negative 2 plus minus square root of 64 over 6. That was a perfect square number. We could evaluate the root and we could simplify this expression to 1 or negative 5/3, which means we end up with rational roots. If you end up with rational roots, that really means that the original equation the equation that we worked in the previous slide could be solved by factoring. So we didn't actually have to use quadratic formula. We could solve it by factoring. How to factor this one? Well, when we already see the roots, then it's easy. We don't have to guess too much. One bracket must be x minus 1, so x minus the root. And the other bracket, normally I would say x plus 5/3. But I'm factoring in integers, so this denominator 3 will be written before the x, and then it's plus 5. Easy to check that when you multiply these two brackets, you obtain the original trinomial. So as soon as discriminant is a perfect square, we know that the equation can be factored. If it's not a perfect square, then we have to use quadratic formula. Here we have a couple examples. We need to determine the number of real solutions without solving the equation, which really indicates to calculate discriminant, because discriminant gives us all this information. So in order to calculate discriminant, we need to know what's a, b, and c. So my first suggestion would be to rearrange the equation to the decreasing form of exponent. So bring everything to one side in decreasing order of exponents. And then we know what's a, b, and c and calculate discriminant. So discriminant in this case is b squared, 64, minus 4a, which is 3, and c, which is 1. So 64 minus 12 is 52. It is positive. So what can we claim? Well, discriminant positive, we have two real roots. The question didn't ask us to solve it. The question just asked us to determine the number of real solutions. The second one, it's already arranged in order. Let's calculate discriminant. B squared 1 minus 4ac. Oh, it's definitely negative. So that means that we have no real solutions. We will have, but only complex numbers, not real solutions. And finally, last question, maybe let's multiply this equation by 9. That will be 9y squared minus, if I multiply by 9, I cancel the 9 with the 3, leaving me with 3, and 3 times 2 is 6y, plus 1 equals 0. It's just easier to use integer numbers rather than rational numbers. The discriminant is b squared, 36, minus 4 times 9. And 4 times 9 is 36, so discriminant is 0. Okay, what does this tell us? Well, it tells us that we have one double real root. One root. In the next example, we practice how to use quadratic formula. So at first, when you look at the equation, it doesn't look like quadratic, but maybe we need to simplify it first. So multiply through the bracket negative 2t squared, negative 4t, bring the 3 over, plus 3 equals 0. I would suggest that we multiply this equation by negative 1. I usually don't like to start with a negative in front of the polynomial, so it will be 2t squared plus 4t minus 3 equals 0. And now we can use quadratic formula. So the roots t, either 1 or 2 roots, are negative b, negative 4, plus minus square root of b squared, 16, minus 4 times 2 times negative 3. So negative changes the sign to positive times 3. Over 2a, over 2 times 2. And simplify this. So what do we have? We have negative 4 plus minus square root of 16 plus 24 is 40. Square root of 40 over 4. And now it would be good to simplify this root. So we could pull the 2 out of 4, because 40 is 4 times 10. Pull the 2 out of the radical, and it's root 10 divided by 4. Remember that we can't cancel 4 and 4 like this, because this 4 is not a common factor for the numerator. In order to reduce anything, we need to factor first. So factor 2 from the numerator, negative 2 plus minus root 10. And now we are ready to reduce the 2 with the 4. So let's cancel this. That will give me 2. And the final answer would be negative 2 plus minus square root of 10 over 2. Those are the two solutions for the first question. Now let's try another example. Here the x, 1 or 2, would be negative b, negative 2, plus minus square root of b squared, which is 4, minus 4 times 3 times 1. Everything over 2 times 3, which is 6. So we have negative 2 plus minus square root of 4 minus 12. So square root of negative 8 over 6. That gives me complex number solution. So we have negative 2 plus minus 8 could be seen as 4 times 2 times negative 1, for example. So we can pull the 2 out of 4 out of the radical. The other 2 has to stay under radical. And we also have radical of negative 1, which is I. So here we have a complex number divided by 6. Again, in order to simplify it further, we need to factor the 2 from the numerator. So we have negative 1 plus minus root 2i, and we can now reduce with the 6. So the final answer is negative 1 plus minus root 2i. The I is outside of the root, over 3. In the next two examples, we'll practice completing the square method. So recall, the first step would be to bring the 1 over to the other side. X squared plus 3x equals 1. Then complete the square of these first two variable terms by taking an x, the same sign, and half of the middle coefficient 3/2, square this whole thing, but then subtract perfect square of the number that we took in a bracket. So it's 9/4 equals 1. Change the 1 into 4 over 4 in order to prepare our number for addition of 9/4. So x plus 3/2 equals 9 plus 4, it will be 13/4. Then we are taking square root on both sides, and we obtain x plus 3/2 equals plus minus root 13 over root 4, which is 2. Finally, bring the 3/2 to the other side under common denominator 2, so it's negative 3 plus minus square root of 13, and we're done. Here it is. In the following example, let's do the same. Bring the 6 over. 4x squared minus 4x equals negative 6. Then divide the whole equation by the leading coefficient 4, which is x squared minus x equals negative. After simplifying, you will get 3/2. Then complete the square, which is x, the same sign, minus, and half of the leading coefficient 1/2. Square it, subtract perfect square of the number that we took in the bracket, so it's 1/4. We can change this number to quarters as well, so it will be negative 6/4, and we have x minus 1/2 squared equals negative 6 plus 1, negative 5/4. Now, when we place the square root on both sides, we'll see that the final answer will consist of complex numbers because we have root of a negative number. So we have x minus 1/2 equals plus or minus, don't forget this, square root of negative 5, which is the same as square root of 5 times I, over square root of 4, which is 2. And final step, bring 1/2 to the other side. So it's 1 plus minus root 5i over 2. We could rewrite this as a complex number that could be written like 1/2 plus minus root 5 over 2i. So that's a complex number form. Here we have a couple applications that will involve solving quadratic equations. The demand for a certain product is given by the formula P equals 26 minus 0.01x, where x is the number of units sold per month and P is the price in dollars at which each item is sold. The monthly revenue is given by R equals x times P. What number of items sold produces monthly revenue of 16,500? So let's see, what do we have given here? The number of units sold, x, and P, which is the price of those items. So price depends on the number of units sold. Now, the next relation that is given is the revenue. Revenue R is the product of price times the number of units sold. The question is, what number of items, that means what is the X that will produce 16,500 revenue? Well, the revenue is known, so we can start our equation by following the revenue relationship. So instead of revenue, we can write 16,500. Then x is unknown. That's exactly the variable that we are looking for because of the question, what number of items? So what is the x? That's what we don't know. So we can multiply x times p, but p is given as a function of x. So using this in a bracket 26 minus 0.01x, we create a quadratic equation. The first thing to solve such quadratic equation would be to multiply through the bracket and arrange all the terms in decreasing order of exponents. So we have here 26x minus 0.01x squared equals 16,500. If we move the x's to the left, then we end up with 0.01x squared minus 26x plus 16,500 equals 0. So we have a typical quadratic equation, and because the coefficients are not very friendly, we are going to use quadratic formula to solve for the roots. So if I start with x, since I expect two roots, I can write subindexes 1 and 2 equals negative b 26 plus or minus square root of b squared 26 squared minus 4 times a, which is 0.01, times c, which is 16,500. Everything over 2 times a, which is 0.02. Now we can use calculator to figure out the discriminant underneath the root, and we end up with 26 plus or minus square root of 16 over 0.02. But that equals to 26 plus minus 4 over 0.02. And finally, we end up with 30 over 0.02, which gives us 1500. Or with minus, we'll have 22 over 0.02, which would give 1100. So what does this mean? Well, it means that x could be 1500 or 1100 items sold. In both situations, we'll end up with the same revenue, 16,500. So we can give the final answer: 1500 items or 1100 items sold will produce monthly revenue of 16,500. And the last problem, a veterinarian wishes to use 132 feet of fencing to enclose a rectangular region and subdivide it into two smaller regions, as shown on the picture. If the total enclosed area is 576 feet square, find the dimensions of the enclosed regions. So we need to find dimensions. What are dimensions? Dimensions are length and width, as on the diagram. Let's look through the information that we do have. We have 132 feet of fencing that was used to build this rectangular region with subdivision. So what is the perimeter? What is the total length of fencing needed for this shape? Well, we took twice the length, here and there. So if I want to write the equation that refers to perimeter, I will say 2 length, and then 3 times the width, plus this width, and that width. So we have 3 times width. And this is the whole perimeter, so it's equal to 132. We have one equation that relates L with W. Since we have 2 variables, we need another equation. And the other equation comes from the information about area. The total area of this enclosed region is 576. But what is area of a rectangle? Well, length times width. So length times width is 576. Now we have 2 equations with 2 variables, so it's possible to solve. How can we do that? Solve the first equation for example, L. I will get 132 minus 3W and divided by the leading coefficient 2. So this is the substituting expression. Then we're going to plug it into the second equation instead of L. So let's put this together. 132 minus 3W over 2 times W equals 576. So now we can notice that this indeed will be a quadratic equation because W's are multiplied by itself. How to simplify it? Well, I would suggest to multiply by 2 to get rid of this denominator. So we'll have 132 minus 3W times W equals 1152. And finally, open bracket and arrange in order starting with the positive sign. So we'll have 132W minus 3W squared minus 1152 equals 0. And I will start with the square term and change the sign. So we can write 3W squared minus 132W plus 1152 equals 0. Now when I look at all the coefficients, it turns out that all of them are divisible by 3. So to simplify our calculations, let's divide this equation again by 3, leaving us with W squared minus 44W plus 384 equals 0. Now let's see if we could factor this polynomial. So I could break the 384 using factor 3 into smaller numbers and see what is this composed of. Since 3, 4, and 8 add up to 15, so this number is really divisible by 3. Let's divide this by 3. We'll end up with 128. But 128 is a power of 2. So this is equal the same as 2 to the 7th. So the prime factorization of 384 is 2 to the 7th times 3. Now it happens that if we break this product into 32 times 12, these two numbers add up to 44 and they multiply to 384. Therefore, our trinomial can be factored into W minus 32 and W minus 12 equals 0. So we end up with the following roots. W could be equal 32 or 12. Now, if W is 32, then from substituting equation, we can calculate that corresponding L would be equal 18. If W is 12, plug it into the substituting equation. So 3 times 12 is 36, subtract from 132, which is 96, divided by 2 will be 48. So this L would be 48. So here we have the two possible solutions, length 18 and W32, or length 48 and W12. Notice that this factoring was obviously this factoring wasn't very easy. Obviously this factoring was not very easy. So the other option would be to apply quadratic formula to the above equation. So we may want to apply quadratic formula, and we'll end up with the same answers. So that will be all for this lesson.